Hey everyone, welcome. I got a new mic and we're going to try it out tonight for the first time and hopefully it's better than that old one. So we'll do 3.8 again and hopefully this time it turns out a little bit better. I'm going to work a couple of the problems that are similar to the ones that you have in your assignments. So let's look at number 9 in 3.8. X equals cosine of the natural log of t and y equals sine of the natural log of t. And so this is a parametric equation because it has an expression in terms of x, a second expression in terms of y, and the third parameter that is brought in is t. So for this parametrization, that's a mouthful, let f of t equal the natural log of t. So then we can graph f of t over here. Where did that come from? To make that better. We can graph the natural log of t, and it's going to look something like this. We have a vertical asymptote here at the y-axis or at x equals 0. I'm going to try to extend that a little bit. So looking at this, ask yourself, what is the slope of the tangent line? What does it look like at any point along this graph? And that's very important. So along those lines, if we take the first derivative, f prime of t, we would get, of course, 1 over t. And this is really nice because in this expression here, t obviously cannot equal 0. And looking at it here, all t, x is greater than 0 for all x. So that kind of tells us what this particle is doing. So because we know that the particle is moving counterclockwise, whenever the first derivative is greater than 0. And in this case, that is when t is greater than 0. So because this first derivative is always greater than 0, this particle is always moving counterclockwise. And notice that it's not defined when t is less than or equal to 0. Okay? Is not defined in those instances. So that's pretty cool. I like that one. So there is number 9. Let's move on then to another one. Let's see. How about number 13? I like that one. So I'm going to stop for a minute and draw a little unit circle and get this set up, and you won't even notice that I'm gone. Okay, here we go. Number 13. So number 13 says, write a parameterization for the curves in the xy plane for a circle of radius 5 centered at the point 2, 1 and traced out counterclockwise. So I guess before we jump into this, we should review a little bit about circles. And that might help us get, just a little more familiar with them. Remember that if we have a circle that is centered at 0, 0, its equation for that is simply x plus 0 quantity squared plus y plus 0 quantity squared equals r squared, with r here and x here and y here. And this gives you coordinates, and obviously you recognize this. Sure, it's Pythagorean theorem. And it would give you coordinates for any point along this circle following that path. And notice I put 0 and 0 here for a reason. Those are the coordinates of the origin of the circle. Okay? Now, or these are the coordinates of the origin, not necessarily the center of the circle. So, and I'll get to that in just a minute. So let's say we move the origin, somewhere over here. Our circle is centered at 2, 1. So let's try to figure that out, what that would look like. Okay, if this were the case, let's say this is 2 and 1. And then our origin would be right here. Maybe I'll make that in blue. There's the origin of the circle. Okay, so now let's see how that would change the equation for this. So now this would be x minus 2, because that's the x coordinate, and y minus 1, quantity squared. And that would get you there, and r we know is 5. So if you're right here, notice the distance here is x plus 2, but we just want this distance here, so that's x minus 2. Whatever x coordinates you have here, you've got to subtract off this part here. Whatever y distance you have to subtract off that 1. So that's why we would do it in this fashion right here, equals 5 squared, and 5 being the radius. So we can put that in now as well. So that would give us, I guess I should go blue to be consistent. That would give us the coordinates for any point on this circle. So very nice. I'm going to move this up here. Keep that handy. So now let's think about how this would go. Instead of x and y, let's, in our minds, think back to when we did trigonometry. The x coordinate here, or the x distance here, I should say, was expressed in terms of cosine theta, and the y was expressed in terms of sine theta. Well, here, and this only worked when we had our unit circle, there was a coefficient in front of each of these that was 1. But in this case, notice our unit circle has grown by a factor of 5. So instead of the radius being 1, it's now 5. So we have to multiply whatever distance we have here by 5. So I'm going to get rid of this 1. I'm actually going to move that a little. Maybe I'll get rid of that too. Doesn't look good. So now instead of cosine theta, it's 5 cosine theta. And instead of sine theta, it's 5 sine theta. And notice one other thing. In this instance, we don't have theta. We have t as our third parameter. So we're going to just say 5 sine t and 5 cosine t. And that will get us coordinates for any point on this circle. So we can have x equals 5 cosine t. But remember, we started at 0, 0 here. So 5 cosine t plus 2, and y equals 5 cosine t plus 1. And that is a beautiful thing. Beautiful. And I just noticed I might have goofed my signs up here. I got to think about that for just a minute. That distance is there. Yeah, these should have been plus. Ignore me. I'm tired. It's too late, but I'm still working. Okay, here we go. So x equals 5 cosine t plus 2. So we go 5 cosine t plus that distance there. And 5 sine t plus 1. And that would get us out there. Yes, that makes sense. My answer is reasonable. And now we'll move on to our last one for this vodcast. Let's do 24. I like that one too, and that's a good example. So I'm going to pause once again. Okay, here we go. Number 24, we have find an expression for speed and the time when the particle stops. We have x equals t squared minus 2t. We have y equals t cubed minus 3t. So remember or look back at this time, just make sure you have it. Page 144, it says the velocity equals the square root of dx dt, which is the derivative of x with respect to t squared plus dy dt, derivative of y with respect to t, also squared, square root of all that. Now, notice, once again, it's just a Pythagorean theorem, again, in a different form. This first part is the x component, and the second part is the y component. And velocity, of course, is a vector, speed with direction. So we can use that. So if I have x equals t squared minus 2t, then the derivative of x with respect to t equals, well, I use a power rule there, 2t minus 2. And over here, oh, it's in pieces. Man, I can make it good. Pretty good. And the derivative here is dy dt equals 3t squared minus 3. Now, notice I did not have to use the chain rule because this one is derived in terms of y and t. dy dt, so I can just use my power rule here. dx dt, I can just use my power rule here. And that's a very important distinction from when we were doing implicit derivations. Okay, so now we can use this up here. Maybe I'll bring that down as we go. Everything's in pieces. Bring it down as we go. So we have this equation here, and for us, the velocity equals the square root of 2t minus 2 squared plus 3t squared minus 3, also the quantity squared. And you can simplify those if you want to, but really you don't have to, because this is something that we can express in our calculator and get a velocity out of that for any value of t. So that works just fine. So that part is the answer to an expression for the velocity. And now all we got to do is figure out at what time t that this particle stops moving. So we know that it would stop when 2t minus 2 equals 0, or when 3t squared minus 3 equals 0. So we're saying when the first derivative equals 0. When the slope of the tangent line is 0, then the velocity is 0. If just for an instant, it's instantaneous velocity. So, well, let's solve this then. We can say 2t equals 2, t equals 1, and over here we have 3t squared equals 3. That means t squared equals 1. That means t equals plus and minus the square root of 1. So t equals plus 1 or negative 1. Now, this is important because we're saying at time t, and we don't have time of -1. So this -1 is an extraneous solution. Mathematically, it's correct, but in reality, it's not. So we can say that the particle stops at t equals 1 second. I think is the unit. I think is the unit. I should double check that. Oh, my box is just not good enough for you all. You deserve a better box. There you go. So I'm going to double check. This was number 24. And speed for the given motion of a particle and any times. Well, it doesn't have units, but I'm going to assume it's seconds. Usually for when we're talking about particles in motion, we're talking about seconds as our unit. Okay, so that is number 24. Quick review there. Here's our expression for velocity, speed with direction, and here is the time t equals 1, hopefully seconds, when the particle is stopped. All right, thank you for listening. I hope this is helpful, and I hope you have questions tomorrow in class. Bye now.